I'm just going to give some quick background and context on the team, and then we'll turn it over for the real meat of the event, some of the interesting work. Shoot, so it looks like host disabled participant screen sharing. Is that something we can enable?
Yeah, I think Richard is working on that.
Okay, there we
Yes,
go.
apologize for that. Yes, now you should be able to share your screen.
Okay, cool. So where do we go? Where's PowerPoint? Here we go. Oh, I have to grant access to Zoom. Stand by. It's telling me now I need the software update. Ugh. Sorry, I should have practiced this beforehand.
That's okay.
System preferences, okay, privacy. Looks like I have to quit. I will be right back. I just had to update, so it was allowed to Zoom. The Zoom app was allowed
Are
to.
you guys using Windows or you have your own operating system?
No. This is a Mac, but
Mac,
most of our meetings are on an internal, or not an internal tool, but an enterprise Facebook tool called Workplace. So we're not on Zoom as much. And I always use my portal. I always use my portal, which is our hardware technology, which is actually pretty cool, pretty good for meetings. So I'll be right back. I'm really sorry.
Sure. So Nick and Sheldon, how long you have been with Facebook? We just chit chat a little bit here.
Yeah, I've been here about 3 years now.
Nice.
Yeah,
are you also based in? I'm sorry. Are you also based in DC or?
Yeah, so I actually just moved, and so I'll be working in the DC office. I was in Menlo Park, California, but then I'll be working with Mark in DC once our offices open back up.
Nice.
All right, I think we're in business.
Mark is back.
All right, so let's go into presentation mode. So hopefully everybody can see my screen. Sorry for that technical difficulty there. So once again, thank you so much, everyone, for the opportunity to come share some of our great work. My name is Mark Bittman. I'm a research data science manager at Facebook, based out of the DC office, or what we call FBDC. Been there just under a year. It'll be a year next week. So I'm told that picture is what the office looks like, though I've never been there myself. I joined just after the lockdown started, and the DC office still hasn't opened yet for COVID. So I was getting ready to book travel out to the West Coast to do my interviews there when things shut down. I called the recruiter and I said, I heard you guys just closed. I guess I shouldn't get a plane ticket. But yeah, excited to get back and meet Nick in person and everybody else. Quick agenda for the evening. I want to give a quick intro, just since we're local and many people may be surprised to even learn Facebook has a presence here, much less like a tech presence. Give it a little bit of an intro to the office, and then share a little bit about the team that Nick, Jiadong, and myself work for, which is called Infrastructure Data Science. And then the fun part will be the two deep dives. So we thought it'd be interesting to share a couple of kind of case studies of some of the work that we do and really go deep here for a technical audience. And then want to leave plenty of time for Q&A. Any questions or inbounds, so please feel free to ask. And if there's something you want to ask along the way, don't hesitate to jump in. We can keep this as an informal conversation. That's how we like to do things. So maybe before that, I'll just give a quick intro to myself. So as I said, Mark Bittman, been at Facebook for about a year. I've spent my whole career in DC. I actually went to school here. I studied physics in undergrad. And was always really intrigued by the notion of using math to solve problems, and so that brought me into physics. And physics was too hard, so I didn't go to grad school for it, and ended up getting a policy job actually here in DC. And went to grad school part-time for computer science because I found myself working on some big quantitative problems, and that's really where I was drawn, but didn't have the tools really to, I don't know, put those problems into practice. Like I remember seeing Python for the first time, and I was like, what is that? So anyways, I went to grad school for computer science. And so I think I was kind of doing data science before the term was coined. I never really knew what to call myself. There was one job where we were like called modeling and simulation engineers because we weren't allowed to be called software engineers. They didn't really know what to call us, but so yeah, spent about 10 years mostly doing like public sector stuff, as many do in DC, and then 5 years after that, working at a managed services company based out of Tyson's Corner. We were basically building and operating large data pipelines on behalf of financial services firms who were like buying up data sets from all sorts of places. And they didn't really have the expertise to not even like handle very large data sets, but even know how to sort of operate data flows or data pipelines at scale. So really like productionalizing data flows and then running algorithms at a production scale, which like most people were able to do it on their laptop, but when you started thinking about actually keeping the lights on those things. So we were a managed services company doing that for largely financial services. And then found this opportunity in Facebook with our integrity group there. And so I've been working with our integrity teams. I'll get into what that means in a minute since joining Facebook. So FBDC, once again, here's a cool photo from the office, but I can't vouch that it's real. I've never been. It's tackling some of our most critical challenges, from keeping our community safe from harmful content to election security efforts. So I was explaining earlier to Tiger, the DC office has grown kind of organically based on some non-technical positions that started here. So like a lot of big companies, they'll have lawyers and lobbyists in place. And that's really sort of how the DC office started. But then out of that came some more technical work. And I think one of the models for like how data science will grow at Facebook is like the engineering presence grows, and as we start building systems and infrastructure and products, then that sort of there's like a lagging effort there. We're like, okay, now we all of a sudden need a team of data scientists there to help support that, and so that's really kind of how that presence has grown. In particular, there are kind of three core areas of technical work that we do in the DC office. The first is called integrity, and that's really about keeping harmful content and harmful actors off the platform. This is, as you can imagine, a particularly relevant topic. It's a huge challenge. There's massive resources going into this in Facebook. They've spent like billions of dollars on this since like in the last 5 years, and so quite literally in growing this practice, not in the DC office alone, of course, but I like to equate that by saying, like, imagine you started a company in like 2015 or 16, and somehow you managed to raise $2 billion, which like would be enough of a feat in of itself. But like, how would you even spend that? Like, imagine spending that much money in 5 years. But there's been a huge effort because it is really important to the company. There's all sorts of challenges that we've been working on. Obviously, the most recent election was a huge one. Everybody got to breathe a little bit at the end of the year last year. But it's a dynamic problem, and one that has lots of interesting data challenges to solve. Another initiative, which is one of the most pervasive initiatives right now in the company, is privacy. And there are some really significant investments the company's making there about keeping user data private, and lots of good data science challenges to solve there. Assessing privacy risk, looking for regressions in privacy, things like that. And then lastly, security. So all sorts of different types of security, from people linking out to malware on the platform to, as you can imagine, threats against the security posture of Facebook. So So those three teams kind of comprise a big chunk of the engineering presence that we have in DC. And for our data engineers and data scientists, we tend to sort of grow as those engineering teams grow. We are hiring in the DC office. We're hiring in the Menlo Park office, obviously. Seattle, New York, Boston are the big ones. Facebook DC still remains one of the smaller ones, but definitely growing. I'll share the positions in the infra DS category, which I'll explain what we do in a minute. Largely looking at more experienced roles. You can get my contact information from Richard, but would love to hear from folks in the DC area or not that are interested in learning more about some of the positions that we have. And then while we all come from that infra DS org, there are other types of other kind of flavors of data scientists as well, where there's opportunities. So certainly interested in meeting folks if there's an interest in coming to join the Facebook team. So would love to connect and share a little bit more about those types of opportunities. So like I said, in DC, other areas in the country, and then relatively recently new, we're now supporting positions that are fully remote as well. So a little bit about the infrastructure data science team. So the three of us come from this particular team. We work in the infra org. So the infra org is kind of like AWS inside of Facebook. So we don't sell our cloud services externally to consumers, but we operate like a pretty large cloud infrastructure globally. And that's, that comprises operating our own data centers. So, we've got hardware, we've got infrastructure as a service, platform as a service, software as a service. And so all that kind of wraps up into the infrastructure organization. And so Infra DS are going to partner with a lot of those teams, whether it's the hardware supply chain team, where to locate the next data center, how do we optimize bandwidth for our streaming video, all the way up to how do we improve the experience of our machine learning engineers inside of Facebook. So kind of at the more software as a service or platform as a service level for like the internal tools that we use to build and operate in Facebook. So I think I took this mission from the website, our wiki for our team, which is we build the technology to connect people all over the world. It's a huge challenge. So we need to build an efficient, flexible, and sustainable global infrastructure. And there are lots and lots and lots of very interesting data science problems to solve there. So a couple of examples of types of work that we do: machine learning algorithms for optimizing CDNs, building statistical models on data center demand. We'll get to a little bit of that later. And designing tools that can detect regressions hidden among billions of time series points. So I see there's a couple of, I think I saw some chat messages, so I'm just going to pause here. I see, yeah, so somebody asked if they could ask questions in the middle. So I'm going to pause here and see if Amy or anyone else has any questions.
Hey, Mark, this is Carson also from CADSEA. This is actually my first time hearing the term infrastructure data science. Should I think about it more like engineer type of role? Is it of engineering nature?
Yeah, so infrastructure data science is like the team, but you ask a good question, and there are different types of data scientists at Facebook. And so in the infrastructure data science team, so that's kind of the domain of the problems that we work on, rather than like the role itself. So most of the roles on the infra data science team are what are called research data scientists in Facebook, and they do have a more of an engineering flavor to them, I'd say. There are what's called more like product data scientists as well at Facebook. So it's like a different flavor of data scientist. And while they may have less building of systems, they're going to be almost like a hybrid product manager. And so they're going to be thinking about how do we have data and metrics to really influence a team's roadmap. and influence growth and target kind of the next market opportunity to take a product. And so we have those in like the, internal tools as well, which are saying like, all right, we have this great new tool. We need to make it grow within the Facebook, the company, and get other teams to adopt our tool and use it because we think it's going to make them this much more efficient or effective. So yeah, different types of role, different skill sets, different interesting problems to work on. So I think some people love that product role where you really are kind of helping to drive the future direction of a team, versus maybe on the research data science side where we're like less focused maybe on like the growth of a platform with things like reliability and efficiency and scalability, just by nature of the types of problems that we solve.
Gotcha. Thanks. That makes a lot of sense.
Yeah, sure. It's a good question.
Hey, Mark.
Hey, Mark.
Okay, sorry, go ahead.
Yeah, I'm sorry. Hi, Mark. This is Amy. I have like a couple of questions. So can you share the presentation after the talk? That's my first simple question. And second question is, can you like share a little bit more details on integrity you talked about in the previous page? And the third question is, how are the problems in the data science team in infrastructure at Facebook DC solve those like 3 big problems you talked about in the previous page, like the integrity, privacy, and security? How you map these specific questions back to the general goals?
Cool. So let me check on option 1. So like as with any external communications, this went through like the slides went through a review, and I can't remember whether or not it said you couldn't distribute them or they could. So I'll check to see if I'm allowed or if I can get approval to share those out. I know Xiaodong's talk is like on YouTube, because he's given it publicly before. So let me check on that. And I think the second question was just go into a little bit more detail about like what the integrity team does. Is that right?
Yes, that's correct.
I'll try to be concise, but you can imagine that there are a number of problem domains for integrity in Facebook. So like hateful content is a category of thing that we don't want on Facebook. Child safety. So there are bad actors out there that are using Facebook's platforms that are being used to manipulate children. Self-harm is a challenge that we have to tackle in the integrity ecosystem here at Facebook, all the way out to counterterrorism, misinformation, vaccine misinformation. There's subcategories of these things. So this big domain of challenges, and there are teams dedicated to building like classifiers, for example, to solve specific challenges there. There are teams building the actual infrastructure of integrity. And that's primarily where we have focused because we are the infrastructure team. So you can imagine lots of events that are occurring throughout Facebook's family of apps. And we have to sort of act on those events and say, does this content represent something that should or should not be actioned? There's a whole human review element inside of that as well. So it's a fairly complex set of actions and behaviors. There's appeals that have to go through. And so all of these things add up to the integrity ecosystem inside of Facebook, and lots of tools, lots of systems that are solving specific pieces of that. And so our data scientists might be working on the classifier hosting platform and finding opportunities to make our models run more efficiently. So like if we could reduce the footprint of an individual model, like what's that going to do to our precision and recall for preventing prevalence of some type of harmful content on Facebook. So that's like one example. Another example is, how do we prioritize content to be reviewed for for human review. So like, how do we triage it? Well, it's in part due to the probability that it's viral times the probability that it's like severe. There are some areas, like I mentioned, like self-harm, which we need to get like super escalated because those are like time sensitive for real world harm. There are terrorists who want to stream their activities on our platform. We have to detect those like immediately and get them taken down. And maybe they're streaming it on another platform that might be then piggybacked and sent onto Facebook. So how do we like get that down, and how do we stop that from spreading, not just in Facebook, but like on other parts of the internet as well? So it's a big business in and of itself within the company, and lots of different areas and challenges to work on. And then could you repeat question 3? So you said, I mentioned the 3 areas of security, privacy, and integrity. And your question was?
Oh yeah, yeah. So my question was, because I think you will explain more in details here. So here you said, look, in infrastructure strategy, you have problems ranges from the CDNs, statistical models, and like tools, detect regression, these kind of things. So
Yeah.
are all these fit into your general goal of like integrity, privacy, and security? Do you have like a one-one mapping? I think you will explain more in details, right?
Yeah. Yeah. Thanks, Amy.
Yeah,
Thanks.
okay.
Let me clarify.
Yeah,
So,
cool.
so
Yeah.
there's the DC office, and the DC office has a specific set of challenges that are more prominent. Like we have more staff there that are focused on solving those or aligned to those organizations. Then we have the infrastructure data science team, which like a big chunk of the infrastructure data science team in DC is on the call today. So we're a smaller presence in DC. But it is a big part of the company. So there are teams throughout, mostly in Menlo Park, California, of course, that work for the infrastructure data science team that are working on these sort of generic types of problems that we've solved. And in fact, most of what we're going to go into today is not specific to privacy nor security nor integrity. So infrastructure data science solves problems throughout the entire ecosystem of Facebook and Instagram and WhatsApp and all the core infra that we have throughout the world. So there's a Venn diagram of Facebook DC and then infrastructure data science, and there's some overlap there, but lots of stuff outside of those two bubbles as well.
Hey Mark, this is Darcy. Can I ask a question?
Yeah.
Hey Mark. We've talked before through email. So I have a question. So you talked about privacy in particular. How much is it related to complying with government regulations, especially in light of a recent act passed in California, asking tech companies to respect privacy more, right? So how much of is this problem related to like complying with government regulations?
There's some of privacy that's dealing with that, and then I think some of integrity as well, but it's a big part of it. So I'm not an expert on the area, but I will say there are lots of well-paid and very smart people who are paying close attention to this, figuring out the implications and putting in place a plan to be able to make sure that we are compliant. So like this started with what's called GDPR, right? And there's teams now that have to make it so that you can permanently delete your data when you request it, versus like a soft delete, which just takes you off like the platform, or the ability to download all your information from Facebook kind of came out of that GDPR. So like there are lots of people who are looking for like how these different rules, and it's getting really challenging because lots of different jurisdictions now are passing different laws on data, and I think public sort of Facebook sort of publicly and how should we say it, conversations in Europe about where data can flow and what the implications are. Yeah, I wish I could give a concise answer, but I'm not an expert, and also there's a lot of complexity there.
Thank you. And on the engineering side, is the nature of work of data scientists, like closely working with engineers to understand the nature of the problem, right? And then, coming and frame it into a data science question and then solve it, right?
Yeah, so let me give I'll give my perspective. And also Nick and Xiaodong, please also chime in. Feel free to chime in. But so I've worked in places where like data scientists are they're in their own org and they're separate from the business. And that has advantages because, I think data scientists generally are very collaborative in what they do. I think because our toolkit is large and diverse, and it's hard to always be an expert in everything. And so it helps to be collaborative. There's always lots of things you can try to solve a problem, and having sort of multiple people working together on it. So it makes a lot of sense to be able to tightly collaborate, especially across disciplines. But being separated from the business can make you more aloof to the actual challenges, and you can lose maybe the business context or the domain understanding that is necessary. And then I've been in places where you're tightly embedded with a team. And I think we have sort of a hybrid model in the InfraDS team, where we do have a central organization that has its own culture. We have our own tech talks, journal clubs. We have a reporting structure that is all data scientists, so that the internal processes exist to collaborate. But we also partner very closely with like a domain team that we're working on. But we move around a lot. So we might be working in integrity one year, and then in messenger infra another year. Nick spent some time there. So anyways, so yeah, the short answer is, we do work very closely with the engineers, but I think we also have a good, strong community as well.
This is very helpful. So you guys are tightly coupled with the business. Yeah, thank you.
Yeah, we are generally aligned. You might have a major and a minor. That's a concept that we have. So you might like major in integrity and then minor in a geospatial project or something like that.
All right.
And I'll add a little bit as well how our team has grown in that regard. So we originally sort of started out as like a consulting group for other parts of the company. But over time, what we found is that a lot of the different partner teams we work with share similar problems. Maybe they all want to do capacity planning. And so what we realized is that instead of people on our team each sort of independently reinventing the wheel each time we have a similar problem that comes up, we started to consolidate some of these efforts and actually provide common services that can be used with our different partner teams. So Xiaodong can probably talk a little more to that. I know he's been doing some work with time series libraries that are being used with a lot of our partner teams.
Yeah, and I guess, for our team, we have different teams. We have a lot of teams across the org. Actually, the infrastructure is a pretty big org right now. I guess we have, high level, two types of teams, vertical versus horizontal, right? Vertical teams, like we do have teams dedicated for integrity, security, like, capacity planning, et cetera. And we also have, the horizontal teams, like for a type of questions. For example, I'm working preliminary on time series analysis. We are, implementing the algorithm and models for time series analysis, which is being used by a lot of other teams or other domains across the infrastructure and even across the company. So, if you are really into specific problems, you can choose a horizontal team, or if you're really into solving, a niche or a domain of problems, you can do like the vertical teams. But we do have more vertical teams than horizontal teams within the org.
Interesting. I have a follow-up. So in terms of career development, it sounds like, it's project-based, right? And then you develop a niche either vertically or horizontally over time, and you have expertise. You become the expert in that area, right?
Yeah, we do have different type of role as an IC or as a manager. So for example, you can do a generalist, like you do a lot of stuff, over the years, and you're pretty good at a lot of stuff, or you can be an expert for a specific niche or area, for example, time series analysis or like deep learning or other stuff. So we do have the flexibility for you to choose, the one you preferred or the direction you prefer.
Thank you. I'll give the opportunity, the floor to someone else to ask questions.
Thank you.
I think we can get back to the presentation, please, Mark. For the sake of time, I think there are a lot of interesting questions for you guys that I would like to. I think we want to go back to the presentation.
You bet. All right. So with that, I'm going to turn it over to Nick.
All right, thank you. And thank you, CADSEA, for hosting us. It's nice to virtually meet everyone. So I'll give a brief introduction about myself. I've been at Facebook for about 3 years now on the infrastructure strategy team. Before that, I actually have a background in chemical engineering. I went to Georgia Tech for my undergrad. And then in graduate school, it was also chemical engineering, but I started moving more to the computational side of high performance computing. I did simulations for lithium ion battery anodes. And a lot of that work, sort of data analysis and modeling and simulation lent itself well to data science. So I started to find that it was a natural transition to go from that high performance computing work into data science. And I actually previously had some interaction with Facebook at Georgia Tech. They hosted one of their first hackathons in 2011 at our university. And so it got me really interested in the type of work they were doing. And so I noticed there were a lot of interesting large scale problems. So I've worked on a few different areas at the company so far with a few different partner teams. I think one of the more impactful things that I've done is working with the messaging infrastructure group for capacity planning. So I'll give a brief introduction about what this team is, what they do, and what the problem that we wanted to solve was. So messaging infrastructure is the group within the company, primarily based in New York, that focuses on building out the infrastructure for Facebook Messenger. And recently they've started supporting the infrastructure for WhatsApp and Instagram as well. So it just started as Messenger, but over time it's grown to accommodate Facebook's other family of products as well. So there's a lot of unique challenges with the messaging infrastructure at Facebook. The primary one being that we have a lot of users, about 2.5 billion, and it's growing pretty quickly. So a lot of the existing approaches for how to handle messaging queues and communications and reliability and these sorts of things at a large scale, they sort of become a different type of problem. So the approaches you might take at a small scale don't necessarily scale up that well. And so we have to develop innovative approaches. Next slide. So the particular problem in this case, and I'll start with sort of the history of what the team is doing, is a question which is basically given 2.5 billion users and the data that is associated with each of these users, which of our data centers do we place these users' data into? So at our company, we have a few data centers. At the time of this project, I think we had about 6 or 7 data centers. Now we're up to about 10 to 12 of them. And so these data centers are located all across the world. They're put in strategic locations that are a combination of different factors related to cost of data center, access to fiber optic networks, latency to users. And so basically, historically, the team has taken these locations as data centers as a given. And what we want to do is provide the capacity and engineering group at Facebook with estimates of how many machines we'll need at each data center to accommodate users. So ideally, we'd like to optimize for user experience first, and then we can handle other things like reliability. So historically, the team has basically used a heuristic for where to place the user data. And this is primarily based off of maybe we say users in each country. We'll just put the user data into one particular data center for each country. This heuristic isn't necessarily optimal though, because we may have assignments for countries that don't actually correspond to the messaging patterns that users use. Ideally, we'd like to minimize that latency for each user. And so the work here started a couple of years ago when the messaging infrastructure team came to our group and basically asked if there is a more optimal way that we can solve this problem. As the company grows and the number of users grow as well, we really want to provide the best experience for each user. And so this group wanted to know how to do it. And so more formally stated, the question is, given a desired user placement scenario, what capacity do we need at each data center? So this is the forward problem. And in the second half of the presentation, I'll get to the reverse problem, which works a little better for our needs. So an example may be that we wish to move 30% of our users from data center A to data center B. And the question is, how many machines do we need at each data center in order to accommodate them? And so what you can see here is a plot over time of how these users, monthly active people at each data center has changed. And so you can sort of see for 8 different data centers or so, the current number of monthly active people. All right, next slide. So the first step of this problem is determining the user placement. And how do we want to do this? There's a lot of different factors that we can consider here. And toward the end of the presentation, I'll get into some of the more recent ones. But the biggest determining factor is the one that minimizes latency, because latency most directly corresponds to the user experience. And if we can put each user in the data center that minimizes their latency, then that's sort of the best experience they can have. And so one of the problems, though, is that not necessarily all of our apps provide location information about the users. For example, for certain phone operating systems, it may not provide where that user is most frequently using their account. And so for these, we'll have a set of default data centers that we can place those users into, namely the data centers that have the most available capacity or the least capacity crunch. For the other users for which we do have location information, we can basically figure out the optimal data center that minimizes the latency for that user. And so for an example here, let's say I look at myself and I look at the latency for me sending a message, and assuming that my user data is in each of the 8 different data centers. And you can sort of see what the weighted latency in terms of milliseconds is for each of these. There's a few different layers of complexity as well. It's not strictly from the user to the data center. We have what are called points of presence. And these are sort of, I'd call them almost mini data centers. They don't really hold data, but they're sort of caching layers between the data centers and the user. So what we do is we do some routing, and we can basically predict the amount of time it takes for a message to be sent from a user through these points of presence and to the data centers. And then we can look at who the users are messaging and where their locations is. And so we can basically compute for all the messages that a user has sent. We can weight that latency across the different messages they've sent. So for example, if I send a message from A to B, from A to C, and from A to E, I can see how frequently I've sent those, and we can weight it based on how often messages are sent to each of them. All right, next slide. So once we have the ideal location determined for each user, we can use that information, we can provide it to the capacity engineering team and say, basically, this is the number of machines that we'll need in each data center to accommodate each user being placed in their best location. But that doesn't completely solve the problem, because user growth changes over time. And what we see is that for different countries and other different things, like whether the user is using iPhone or Android, we see that the growth actually changes over time. So for example, in the US, we may have relatively slower growth now. Initially, when Facebook first came out, we had some very quick growth. And so there was a lot of activity in terms of users increasing their usage of Messenger. But over time, this has leveled off a little bit. In other countries like the Philippines, though, we see continuing increases in usage. And so it's not equal across all countries. And so the main reason this is a problem is because for our capacity pipeline, we need to have a system in place to determine what capacity we need well in advance of actually having that capacity. So this is typically 6 months to a year out in advance. We need to know how many machines we're going to need in order to accommodate all of the user growth. So how do we do this? So what we have now after step 1 is we have the best data center to place each user in to minimize their latency. And then from there, we can develop forecasts to figure out what that data center's expected capacity would be 6 months or 1 year from now. And so the way we do that is we take the country that's associated with each user, and then the demand of that, the distribution of that messaging demand over time of day, and we can basically forecast then what that peak demand is going to be. So each country has a different peak in terms of time of day for messages sent. Maybe in the East Coast of the US, maybe that peak is 7 a.m. but maybe on the West Coast, that's 3 hours sooner. And then for countries maybe like India, there's different usage patterns. Maybe we see people in other countries using Messenger more at night. And so every country has a different peak for when the most messages are sent. But our data center has to handle the maximum peak load. So we're actually forecasting to prepare for the combination of all these different peaks. So we develop a forecast at the per country level. And then for each country, we pick that basically the distribution of sends during the day. And we can add them up across all the different countries. And that gives us the maximum anticipated peak load. And so this demand forecast is done both for organic growth across countries and across interfaces like Android versus iOS. All right, next slide. So what we have now is we have the ideal placement for each user, which data center they would be best served by. And then we also have what that data center's anticipated growth will be. So how many machines we need to order 6 months to 1 year in advance to handle that new growth. But that's not the only problems we have. We have to also consider the situation of disaster readiness. And so for various reasons, we can have data centers that go down. This can either be potentially due to political reasons, perhaps internet is cut off for one country. It could also be due to natural disasters. We have things like hurricanes, tornadoes, power outages. And so we have to be able to prepare for the situation that any given data center will go down. So in this case, what we do is we determine the next best placement for each user. And what this is, so each user has a primary location where their data will be stored. And we also have a secondary backup queue. And so these queues are used in the event that there is a data center outage. All of the traffic is basically routed to these backup queues. And so the next question though is, does our capacity necessarily scale in terms of number of users? That'd be a nice relationship if it was basically just 100 million users in one location, had a linear relation, but that's not actually the case as well. What we find is that there's a nonlinear relationship between usage activity and the load. Actually, it looks like I've gotten a couple of questions, so I'll go ahead and answer these. So from Amy, how do you define demand and what forecasting models do you use? Yeah, so those are very good questions. With Messenger, we have a lot of different services. We obviously have the message sending, but we also have things like people sending images to each other, videos, pictures. We even have things like read receipts, whether a user saw a message. And not only that, but demand is actually defined not in terms of one message sent, but in terms of the number of recipients that a message is sent to. So if one user in a group chat sends a message to 10 different people, that's actually 10 different messages that have to be routed and sent. So what we use is something called sends plus fan out, which is the number of recipients that a message was sent to. And this is our primary factor for determining the load on a data center. Like I said, we have some secondary things like message reactions and likes and read receipts, but these are very small in terms of contributing to the overall processing load. So our demand is primarily message sends plus fan out. For the second question, what forecasting models do we use? So this is probably something Xiaodong could answer a little better now. At the time I worked on this project, we used a pretty simple model actually. So we split the forecasting into a few different components. We had what is called the smooth organic growth. And so for each country, this is a steady pattern that's smooth that we see. And so this could be forecast using any of the typical forecasting methods, Holt-Winters, ARIMA, even just, I think the team was using linear projections before we joined. But there's also a seasonality component. And so message sends follow patterns that have daily seasonality, that have weekly seasonality, and even seasonality over year. For instance, we see growth at the beginning of the year. It levels off about mid-year, and then toward the end of the year, that growth continues spiking as well. More challenging, and I'll get to this a little bit later in the slides, is anticipating special events, holidays. These cause a big problem for our forecasting, but I'll get into that a little bit more in the later slides. And I have a second question from Yi. Are step 1, 2, and 3 ranked in terms of importance of goals? Not necessarily. So these steps are ranked in sort of the order that we've done things in the past. And this was the original approach we used. In the second half of the presentation, I'll get to the current approach, because what I'm presenting here is basically, given where we want to place users, how much capacity do we need at each data center? But it turns out a better model is actually, this is the amount of capacity we have in each data center, and where should we place the users based on that? So I'll get a little bit more into the priority of the goals in a few minutes. And feel free to go ahead and interrupt me with a question as well, if you'd just like to ask one. All right, so computing the CPU needed. So going back to this, in terms of like the messages sent plus fan out, we do load testing to determine how many machines are needed to handle this. And like I said, it's not a linear load. And so the way we do this is we have a set of machines that are provisioned, and perhaps we have 100 machines. And so what we start doing is we direct the load for the queue into these specific set of machines. But we start out slowly, and then we increase it linearly. So maybe we have a few million message sends per second, and then we increase it to 2 million, and then 3 million. So as the amount of traffic directed to these machines increases linearly, what we do is we monitor the CPU utilization and the memory utilization, and we try and back out that relationship. And what we see is that as the machines start approaching maximum load, once they reach about 85%, the relationship becomes heavily nonlinear. There may be thrashing and other considerations. So what we do once we reach about 85% is we stop the test, and we use that basically as our capacity. In other words, at 85%, that's the number of queue insertions per second that one machine can handle. And this changes over time as well as usage patterns change. So we periodically run these load tests to figure out basically how many machines we need for a certain amount of traffic. So then we take this CPU usage based on the load, and we convert it to number of machines. And then we have a lot of different hardware types across the company as well. So we have what is called a relative compute unit, which is a factor for converting perhaps older machines with older processors. How do we relate that to a newer machine with a newer processor? So we have a system for normalizing all of this to determine how many machines of each type do we need to provision. Next slide. All right, and so what are the applications of this? Like I said, this in the forward problem, we have a desired location for each user, and we provide the capacity needed to meet this. And the most common application is special events planning. So this is typically holidays. And for Facebook, our biggest event to anticipate is New Year's Eve capacity planning. So this is the biggest one, because this is when we see our heaviest load on Messenger. And as you can imagine, it sort of shifts each hour across the world. And so in this case, what we do is we basically sort the countries that are associated with each user, and we predict the demand at each country level or each time zone as well. So like in the US, there's 4 time zones. So we can anticipate for each midnight occurrence at each time zone, what that peak load is going to be based on the number of users in each data center. Hello. Yes. Does someone have a question?
No, I don't think so. Please continue.
All right. And so for each data center, then we have an anticipated load at New Year's. And what we find actually is that most of our projections, we don't actually have enough capacity to handle that. So what we can do is in advance of New Year's Eve, we can shuffle the users around to lower the load and even it out across data centers. So in this case, we're sacrificing latency a little bit in exchange for meeting peak demand. And we also want to have some buffer there. Because the forecasts aren't perfectly accurate, we may need a little bit of extra room. So we take peak load and we add like 20% beyond that to account for any unexpected load at those times. And then in advance of New Year's, about 2 weeks, we can reshuffle the users' placements. And then after New Year's Eve, we can move them back to their more ideal locations. So it looks like there's a question from Sasha. How often do you usually reshuffle the placements? Any cost cause? So I'll get into that in just a minute, actually. These applications are also used for the new data center turnup. As we're adding more data centers across the company, each time we add a new one, we want to rerun these calculations. Perhaps the new data centers are in a more optimal location for each user. And so we want to compute which users we should move to that data center. And we sort of want to ramp that up over time gradually to make sure nothing goes wrong. And so for this particular application, you can see that we moved 850 million users, queuing primary locations to data center E, and 510 from data center F to B. And what you can see in the plot here is sort of what the expected demand, our message sends with fan out, look like at each data center after the ramp up. All right, next slide. So that was the forward problem. That's historically how the messaging infrastructure team has done it. We are given users and we want to specify what is the best location to put their data. And then we tell the capacity team how much capacity we need to handle that. It turns out that actually isn't optimal for our company because there's a lot of other different systems that are running as well. And so what the capacity engineering team wants to do is optimize for all of the different systems that are used at Facebook, primarily handling web traffic, video, and everything else. So they need to balance all of these needs. And so what works better is that basically they provide us with sort of a fixed capacity available for each data center. And we have a little bit of wiggle room there to tell them what would work better. But generally, the reverse problem is that given available capacities at each data center, we want to move each user into the best data center at that point. And so one example is for our 7 or 8 data centers, we have these available capacities in terms of number of users. And so we want to figure out for each user which data center to put them into. Next slide. All right, and so at a small scale, this is actually an easy problem to solve. We have an optimization problem here with a cost function. In our case, the cost is minimizing average latency. And so what we have is a matrix, 1 row per user and 1 column per data center. And this is basically just the latency for each user sending messages to that data center. And so this is our cost matrix. And what we're looking to find is a placement matrix. 1 indicates the user is placed there, and a 0 indicates the user isn't. So this is basically just a permutation matrix. And we want to place each user in their best data center subject to the capacity constraints. And so this is just a simple integer linear optimization problem, which could be used solved using standard solvers like CPlex or MOSEC. The problem, though, is that we have 2.5 billion users, and you can't actually use these approaches for that many users. Your optimization problem would never complete. So what we started with is some heuristics. Can we come up with a method that handles this many users and still gives a relatively good local optimum?
I use that word a lot.
Oh, can I ask a question?
Yes.
So this optimization is based on a fixed number of data centers. So assume we're like out of capacity, we're adding a new data center. So what do we do?
Yeah, I'll get to that in a little bit, but for a quick answer, what we do is we have continuous user movements where we sort of recompute the optimization at each time. And we also want to consider constraints related to reliability. New data centers typically have some issues and some kinks that may not be ironed out yet. And so what we do is we combine a gradual ramp up of each user into their new optimal location. And so we can sort of artificially limit that capacity on the new data center. So if the data center is available and ready to go, we can start it out maybe say 5 million users. And then over a period of a few weeks to a month, we can ramp that up to its full capacity of 300 million. And so we'll occasionally rerun this problem, this optimization problem. And I'll get into that a little bit more.
Oh, okay, thanks.
All right, next slide. Yeah, so the continuous user movements. So let's say for a fixed set of users, we have now the best data center that meets the constraints and the best secondary data center for each user. So this is good for a fixed situation, but like I said, we have things like organic growth for each country over time. We have users that actually move and change their location. If a user has moved countries, then maybe they're suddenly in a suboptimal location. We have new users joining, users leaving. And so there's a lot of different things going on. And like you mentioned, we have new data centers as well. So we need a system to sort of refine this on a continuous basis. And so in an ideal case, we would just run this optimization problem every day. and then reassign users to their new location. But there's a few problems with that, which is that each time you run the optimization, the user may be assigned to a completely different location. This problem has many different local optima. And when a user is placed in one location, they may be in a different location the next time you run the same exact optimization problem. So what we want to do is add a penalty function actually to moving users. And so if their new best latency is a big enough difference, then we'll have a low penalty. But if the latency change between data center A and data center B for a particular user is small, then that's going to be a high penalty. And so basically we rerun the optimization on, for instance, a weekly basis with this penalty function applied for moving users. And then that gives us a smaller number of users to run to keep the system optimal. And so we use a heuristic to start this, which is basically computing the best data center for each user. We want to keep the maximum number of users with the highest cost. And then for the users that sort of overflow, we'll compute their next best data center. We'll go back to step number 2 and repeat the process again. When there's no overflow at each data center, in terms of like number of users beyond the capacity, we can say that process is complete. So we've actually found this simple approach works sort of well. We've since refined it a little bit more. And the refinement is in terms of, we've actually sort of gone back to the integer linear programming problem, but what we do is cluster users instead. Next slide. All right, and so, yeah, that's the end of the presentation, but since I've worked on this problem, there have been a few updates I want to go over with as well. So what I've mentioned here are some simplifying assumptions. So when I say we want to optimize user experience, what we're doing is just using things like average latency. But average latency may not actually be the best metric to use. Average latency may not consider a user that's very important, that sends a lot of messages across Facebook, but they're sort of anomaly. So maybe we think we want to minimize the worst case latency. But then the problem with that is that you may end up with really suboptimal locations for everyone if you're minimizing worst case latency. So over time, over the past couple of years, we now have a team of research data scientists working with messaging infrastructure to optimize this more thoroughly. We can do things like psychometric experiments to determine, is there some sort of minimum latency threshold? Maybe below 30 seconds, a user doesn't notice the difference. And then we can basically plot the latency versus user interaction with Messenger. And we can determine the point where that user interaction starts dropping off. And then we can weight users by how frequently they use the app, perhaps how important it is to have a particular user have a good experience. And so there's a different additional sorts of factors that we consider for this optimization problem. And so let's see, another question. Are you using AWS data centers or Facebook owned ones? So Facebook maintains our own data centers. And actually we have a section on our website that sort of shows how we set these data centers up. Our data center infrastructure is actually open sourced. The way that we set up basically the centers, and they're very energy efficient. I believe we're now carbon neutral. So you can check out the website to sort of see how we run these data centers and how we set them up. And it's really interesting. So I'd encourage you to check that out.
It's called the Open Compute Project, and Facebook's a founding member. There's a number of other vendors and participants, but yeah, it's like from the data center, building down to the compute and the layout of the racks is all open source. Pretty cool.
Yeah, and so I'd like to thank the messaging infrastructure group that I worked with, Thomas, Patrick, and Jeff. We have a very close collaboration with the software engineers, so it's sort of a back and forth between us providing sort of research and input into these decisions, and the software engineers telling us what's feasible and what sort of trade-offs we may have to consider. So for any other questions, I'm not sure if we want to take them now or wait until both presentations are complete.
Why don't we keep moving for the sake of time, and if there's any lingering questions on this particular topic, we'll get to those at the end.
All right, thank you. And I'll turn it over to Xiaodong.
Cool. Hello, everyone. My name is Xiaodong. I'm a research data scientist at Facebook in the same org with Mark and also Nick. So I guess this is the old slides we have, because you can tell from the date on the left bottom corner. But this is something we have done in the past summer. The title is large scale forecasting and self-supervised learning techniques is all you need. So I'm going to give you more details about the technique itself and also how we apply it to the real world applications at Facebook, right? But before that, I can give you a little bit of context about myself. I joined Facebook, I guess, 2 years. And before then, I was an intern and I was in the same team in the internship and also the full-time after I graduated. So before then, I got my PhD degree in statistics from the University of Georgia. So I spent 5 years in Georgia. And before then, I studied math in my undergraduate college in China. And I guess there's some funny connection for me and also the DC, Virginia area. I visited DC, I guess, 2 or 3 times before as a visitor. And I also visited there one time for a computation, actually. I know there's, some folks today are from Capital One. So that is, I remember it's a competition held by Capital One. It's called modeling computation or something like that. So then was 2016, I believe. So our team won the first place back then, but that was a very interesting trip to the DC and Virginia area. I remember it's called McLean or something. So anyway, let's back to the topic. I'm more than excited to give you more details on the work. Next slide, please. Cool. Here's the agenda. We have for today's presentation. I'm gonna first give you some high-level overview about what I have done in this work, and then I'm gonna give you more details about model selection and hyperparameter tuning with our techniques, and then I'm gonna discuss more about applications and results with the techniques we proposed, and also some future directions in our team. Next slide, please. Cool. Here's the overview and also the statement of the problem we want to solve. So we're interested in solving or forecasting millions of time series data with very low latency. And this is some requests from our partner teams, and they do have a lot of time series data, and they want to forecast them with low latency, or or update the forecast very frequently. And the exhaustive model selection and hyperparameter tuning is not feasible, apparently, because when you have millions of times data, you run the model selection and hyperparameter tuning for different choices of models. That's really slow and not efficient. So and now we're thinking about, hey, instead of training individual time series models, no matter ARIMA, SARIMA, or other fancier time series model, can we predict the best model and even the parameters for a given time series data, right? So instead of exhaustively tuning and training those models, if we can really predict the model we want to use, or even the parameters we can create for this model, that will be super interesting. So the way we're thinking about this problem is, hey, given a time series data, how are we going to extract some features out of this time series data, right? So basically, we can define some sort of characteristics or statistics of the time series data. Simpler ones like mean, variance, median, those simple statistics. Fancier ones or more complicated ones like strings of the seasonality or strings of the trend, etc. So at the end of the day, we can define 40, actually right now 60 or even 70 different types of statistics to describe the time series data, right? And then now the problem is, hey, given the time series data and also after extracting all those features from this time series data, can we really predict the best model or parameters for this data? Actually, the answer is yes. Next slide, please. So a detailed overview, right? So in short, we propose a self-supervised learning framework for forecasting model selection and also hyperparameter tuning for an extremely large collection of time series data, so TLDR. And for model selection part, based on our empirical evaluation, it provides very accurate forecast using much less running time. So basically 75% less than the typical way if you run exhaustive model selection and hyperparameter tuning, right? And for hyperparameter tuning, it provides a much faster solution while maintaining a good accuracy. We're gonna go into more details in a few minutes. So it's definitely a game changer for forecasting at scale because we do have a lot of applications which require us to do forecasting for a very large number of times data. And before that, we have to do it manually, do the exhaustive tuning. And now we have the SIL framework, and it's really a game changer. Next slide, please. And the first section we're going to talk about is model selection with self-supervised learning technique. So here is a very high level description about the procedure, right? How are we going to do model selection with SIL or self-supervised learning techniques we have. So it mainly has 3 components. We mark it as a different color, right? So the first component is offline training data collection. And the second part is training a meta learner, or we call it self-supervised learner right now. And then the online part is make inference for new time series data or given input time series data, right? So let's look at let's first look at the first one, right? The offline part of the training data collection. So assume we have a bunch of time series data that are available on hand. So for each time series data, we have to tune every single candidate model we have. Let's, for example, we have 6 candidate models here, from our in-house model perfect to very classical statistical models like ARIMA or SARIMA, those models. For each model, we run exhaustive parameter tuning over the model and the given data, right? And then we identify the best model, right? For example, for perfect, we identify a combination of the parameters that can achieve the best performance, and we call it best perfect, right? And for ARIMA, we have the best ARIMA performance model, right? For the given data. Let's assume, we only have 1 data for now. And then after you calculate everything and you have, the best model for every individual model, who's the winner. For example, theta model is the winner. And then our best model here is the theta model. And now you actually have the label, right? The label is theta for the given time series data, right? And then that's our response, or that's our label actually. And what about the, the predictors? Predictors here is the features I mentioned earlier that are extracted from the time series data. So given the features on the top and also the label or the target in the bottom, we can actually train a very naive classifier, right? It's kind of very simple multi-label classification problem. So now in the future, for any given time series data, in the online part, for new time series data, the only thing we need to do is, hey, we need to first extract the features from time series data, just like what we did in the offline and also the model training part. And after we get the features, we fit the feature into our classifier, and then we predict the model. So for example, given a time series data, after you try the feature and make the inference with the pre-trained classifier, it tells you, hey, hot winter is the best model you can try. And then you don't have to try all the, let's say, 6 models out there. You simply call hot winter and then produce the results, right? So that's the model selection part. In short, the input is time series features that are extracted from the raw time series data, and the output is the best model we can predict, right, for given data. So I want to pause here for a moment in case you have any questions or comments for this framework.
Hey, Xiaodong, yeah, this is Simon. Can you hear me?
Yeah, I can hear you.
Sure, yeah, Xiaodong. So one question. So basically, this is a 6 model here. However, each model, you have the very different setup. For example, ARIMA, you can have different P, different Q, different I. So basically, you will face much complex than just select with this 6. So want to know how you kind of also handle that complexity. Yeah.
That's actually a very good question. And this is actually one of the motivations why we want to develop the framework, right? So as I mentioned before, the exhaustive tuning happened offline, even though it's very slow, but once it's done, we got the label, right? So for example, we do this exhaustive model tuning for, let's say, 1,000 time series data, and then you got 1,000 observations with the time series feature and also the best performing model. And then after you train the classifier in the future, even though you have 1,000,000 time series data, you don't have to run the exhaustive parameter tuning. You can simply use the pre-trained classifier model, then directly do the prediction, right? And then the latency and also the runtime is really slow. But of course, to obtain the label or the target, we must run the exhaustive tuning. But a good news here is from our evaluation, our empirical evaluation tells us about 1,000 or 1,100 times data is good enough to get a pretty good classifier with our internal data set. So which means you don't have to run exhaustive tuning for, let's say, 1 million times the data to be able to get a good, perform the classifier. Yeah. And the good thing is the online part is really fast, right? You can simply call the pre-trained classifier model and then call it, feed the data into that. Did I answer your question?
Yes, thanks a lot. That's really kind of very new to me. Okay, would like to learn more when you give more presentation. Thanks, that's clear.
No problem, because we really care about the online part, right? So the offline part, that's kind of a trade-off we have to do. Yeah. Any other questions?
Yeah, just want to understand it correctly. So just piggyback on the previous question. So the response is it just the name of the model, or is it also with the parameter space as well?
Very good question. So for this framework, the target is simply the model. You can think it's a string, right? It's a model. And then we have an additional framework to do, hey, given the model you selected, how can we predict the parameters? So that's the second framework I'm going to talk about. But this is a very good question.
Hi, Xiaodong. I do have a question here.
Sure.
You probably talk about, is the best model self-selected from the 6 model? It's one of them, or it's an ensemble of the 6 best models?
In this framework, is an individual model selected from out of the 6 models. For example, in this case, we don't use ensemble in this framework, but of course, ensemble is a way. And I'm going to talk about the potential applications of how to apply the techniques to ensemble model to further improve the performance.
Got it. Yeah, thank you.
No problem. Any other questions? If not, we can. Okay, I see a message through the chat. Oh, MacLeod it is. Okay, I'm working at. Okay, yeah, good to see you here. Anyway, we can move forward. Next slide, please. Here is the performance evaluation, right? With the first framework I just discussed a moment ago. And then the first comparison we do is compared with exhaustive model selection method. Then is you basically run exhaustive tuning for every individual model for every single data. And with 6 candidate models, we decreased the computing time and resources by 83% from our empirical evaluation. It's a pretty clear and big winner. And the second comparison is compared with using a pre-selected model. So what is pre-selected model? Usually when people do forecasting, they already have the model in mind. For example, a lot of people within Facebook, we have the in-house perfect model, and people don't directly go with perfect model and then do the tuning or whatever, even use the default parameter, right? Or probably people from more like a statistical background, they trust the Serima, Hot Winters, other models. This is their go-to models, right? So the comparison here is, let's compare the model selection results from the self-supervised learning method or meta-learning method versus simply using individual pre-selected model, right? That's a comparison setup we have, and our metrics is a MAPE, mean absolute percentage error. So the conclusion is, we used almost the same computing time resources compared with using a pre-selected model, but we decrease the MAPE. That is the metrics we have a lot, right, by a large margin. So if we look at the results here, we do have the numbers for both training set, which is we train the model with the exhaustive tuning offline data set versus test set, right, out of sample test set. And we also have the forecasted MAPE and also the improvement. Then is a MAPE decreased percentage, right? So the first column is actually the self-supervised learning results we obtained from the framework. And then afterwards, the 6 individual models, we assume the user is going to select by default, right? So the result is actually pretty good. By leveraging the self-supervised learning techniques, the model selection techniques, the model we selected, the results, for example, the first column you can tell is 0.08 of the MAPE versus other competitors like Perfect is 0.11, Serima is 0.12, etc. And if you look at the percentage, it's kind of 22% improvement over the second best model. That's actually the Perfect model, I believe, in this case. And if you look at the test case, the similar pattern still holds, but the percentage is definitely much lower. So the improvement is kind of 8.5%. improvement, or in other words, the MAPE decrease percentage compared with the second best model, that's still perfect in our data set. So any questions for the numbers and also our experiment setup?
Yes.
And also, yeah, go ahead, Amy.
Yeah, I may show my ignorance here. So how, I mean, theoretically, how does the SSL, like a forecast MAPE, is less than, I mean, every single of the model? So
yeah. This is a very good question, right? It's kind of idea of ensemble, but let's say, assume we have 1,000 parameters data, right? If you always use one model, sometimes you got good results, sometimes you got better results, right? We have no idea. And then on average, let's say perfect is 0.11. But for self-supervised learner, the ideal case is every time we can always pick up the best model for the data. You always pick up the better one, right? Compared with, the rest of them. So on average, let's say 1,000 times data, you do the inference, the results is actually better. It's kind of idea of ensemble, but it's not ensemble actually, right? It's not an evaluation from 1 times data. It's the evaluation from 1,000 or even more times data. So that's on average. This is why we call average MAPE. It's not a MAPE for a single times data. But your intuition is correct. For 1 times data, the best that we can do is actually the individual model, right? Because we're still using the individual model. We are not using a different model to do the forecast. That is the best that we can do. But on average, that's not the case.
Got you. Because you always, that would be like the average of the minimum over 1,000 like samples.
Ideally, correct. But from our observation, is actually we cannot always pick up the best one, the so-called best one, but we usually can pick up the best or the second best one. But that's already very, very useful.
One follow-up question. So for every iteration, do you run all the 6 of the model, then choose the one in the SSL algorithm?
Good question. I guess we only run the exhaustive tuning in our offline preparation time period. So after we obtain the training data, we never do the exhaustive tuning anymore because we already train the classifier, right? So in the future, you have the only thing you need to do is do the classifier.predict and give them
you don't
the
need
features.
to go through the exhaustive hyperparameter training, but you still need to run through each of the 6 of the model.
Correct. That's correct. Yes.
Yeah. Okay.
That's right.
Yeah, thanks.
No problem.
Hey, yeah, I have one question. So you mentioned so SSL gave you freedom to choose different model at a different time point. So for on average, do you think how long one model can last? So for example, one model can last best for 1 month, or they can last for years. I know it's hard to say, but based on your observation, how long the winner can keep on the top 1 position?
Actually, this is a question from one of our partners when we presented the work for the first time, because they care about, hey, if you change the model every day, that's very dangerous, right? Because they will not trust you anymore. Because you change the model every day, that's not a good signal. So we really do the evaluation. For example, let's assume, we do the back test, right? Let's say have our predicted model changes. Actually, in short, I believe 85% of the model, they don't change for, I guess, 2 years. That's our evaluation period. But we do see 25% of the model, let's say this month versus next month, our best model we predicted is different. So in real world, the way we do is, as long as we pick up the best 2 or 3 models out of all the individual models, that's fine. We don't change the model. We want to make it consistent, ahead of like the pure performance. But this is a very good question. We got the question from our business partners, before.
Okay, yeah, thanks a lot. One follow-up question. Maybe that's a little bit technical. So, you actually follow the timeline to pick different model. So that's also time series model. So time series model that's actually have time dependency. So for example, in this 2 year, you choose one model. In next 2 years, you choose another. But if you, for example, lose that other 2 years, you do not have the full picture. So time series actually need you to take a look at all the data through all the time. So I know that's maybe that's not so clear, because I'm thinking if you cut the full time into small piece, how you kind of, even on your offline, how you have the very accurate, comprehensive parameter estimation.
That's correct. So theoretically, the parameters we selected through the exhaustive tuning offline, period is not 100% accurate. For example, probably, the best parameters are not actually the best parameters we have, right? But that's actually the best that we can do from empirical evaluation, right? And also another question that is very interesting is, as the time goes on, the model could be changed. For example, when COVID happened, a lot of metrics are going to have really weird patterns, right? So, it's very easy to understand, the model we selected from the SL framework is different from, let's say, the pre-COVID period. And that's very common, actually. Yeah. But that really depends on the specific use case or their requirement. For some requirements, they don't care about the model you selected. They only care about your forecasting results. But for some use cases, they feel like, hey, the methodology has to be consistent or has to be explainable to the partners, right? For example, why the forecasting results look like this, how would you explain? And probably perfect model, you can do the decomposition. You can explain, oh, what's the change of the seasonality? What's the change of the trend, et cetera, et cetera. And then you can explain. But for some other black box models, it's really hard to explain. Yeah.
Yeah, Xiaodong, thanks a lot. I know I have a tough question. Thanks, you handled that.
No problem, no problem.
So,
I like your questions.
Actually, I want to say, also glad to know you graduated from University of Georgia, same as me. So.
Oh, really?
Yeah.
Oh, we should talk. We should chat.
Good.
Yeah, we should chat afterwards.
Yeah.
Yeah. I spent 5 years there. I really enjoyed the time there, actually. Yeah. Cool.
Oh, hey, Xiaodong. May I ask a quick question about the performance matrix that you select?
Go ahead.
So I noticed that you use MAPE for your offline evaluation. So do you also propose some like online matrix, meaning that just to monitor your model performance after pushing it online, or some like business related matrix which you're gonna present to your partners, partner teams? Yeah, thanks so much.
I actually didn't include here, but internally, when we do the real-time forecast, actually a lot of stuff we do is weekly or daily forecast. And we do have the monitor system that can monitor the changes. In that case, we have more than one metrics, right? We have MAPE, SMAPE, MAE, other metrics as well. So, and also that's for forecasting purpose. We also apply the forecasting techniques into the detection space. That's a real-time detection problem, right? For example, every few seconds or every few minutes, we do the forecast and we compare the real value versus the forecasted value, whether we want to raise the alert or not, to for the metrics owners or time series owners they are interested in. Yeah, that really depends. But within this context for today's presentation, we only use MAPE. In real world, we use more than one metrics to compare. Did I answer your question?
Yeah, that makes perfect sense. Thanks so much.
Thank you. If there's no more questions, let's move forward to the second framework, the hyperparameter tuning. Because we already do the model selection. Let's assume, given data, model A is the best model. And now the natural question you're going to ask is, am I still have to do the hyperparameter tuning, run exhaustive tuning for a given model or not? The answer is not. We can actually train another learner to predict the parameters for you, right? That's a second framework we have. It's called SLL HPT, hyperparameter tuning, right? So similarly, we have offline model training and also the online part, right? So for the offline part, given a time series and also given a model, we do exhaustive hyperparameter tuning over default search space. We do have default search space for the individual forecasting models, right? And then your target is not the best model anymore. is actually the best parameters for a given model. Let's say for a RIMA model, we have PDQ, right? And then you have a multi-dimensional response, PDQ, right? Let's say 211 is the best performed combination of parameters for the given time series data. And then you have such label. And the input or the predator is the same. So we are still using the time series features we extracted, similar to the previous framework. And now we cannot use the classifier anymore. It's not a classification problem. It's a multitask problem. So multitask, I mean, for example, for let's say a RIMA, you have 3 response, P, D, and Q. You can think about, oh, it's kind of all the PDQ are integers, right? And you have constraints on the value of the parameters. Sometimes the model has categorical, parameters, also have like a continuous parameters, and you don't have a fixed number of the parameters. For example, a RIMA, you have 3 parameters, but for other models, you probably have 10 or even 20 parameters. At the same time, you have to modeling or predict, right? So now the meta learner here is not a classifier, is a multitask neural network. And then the online part is still the same. Given the new time series data and also the model you want to try, we just fit the features into our multitask neural network. It's a pre-trained model, and then we're going to predict the best parameters for the model and the data combination, right? So in short, as I outlined in the bottom of the slides, the input is the time series feature, and also the output is the best hyperparameters of a given model. It's a multivariate. And it's a new perspective for hyperparameter tuning, right? You don't have to try everything, random search, grid search, whatever search method. Simply, you are leveraging a supervised learning perspective to predict the parameters in the context of a time series forecasting, right? Any questions here? I also want to pause for a second to answer any questions before we jump into the evaluation on experiment results, right?
Hello, Sheldon, can you hear me? Yeah, it's one here. I'm from CADSEA. So I think this is the right place to ask a question about the parameter tuning. So in your framework, you use exhaustive one, right? Have you tried a random search or even Bayesian method for parameter search, because they're much faster and probably get roughly similar result?
Yeah, you actually got the point. Actually, in our own implementation, we run all of them: random search, grid search, and Bayesian optimization algorithm. And actually, in Facebook, we actually have an in-house Bayesian optimization platform called AX. It's also open source software on GitHub. You can actually check that out. We were using AX for our Bayesian optimization techniques, and random search and grid search we implement by ourselves. So, but as a purpose of a demonstration, we do exhaustive tuning here. Yeah, cool. You got the point. Yeah, it's a very good question.
Thank you. So, how about you give me some point to the resources you mentioned after the talk?
Oh yeah, of course. Yeah. I'm happy to. I'm happy to. Yeah.
Thank you.
And also, this is actually a part of our I guess 2 years effort to develop the time series analysis Python library. And the good news here is we're going to open source the library very soon. I cannot give more details about the library itself, but these techniques is gonna be the a part of the algorithm and models we're going to open source very soon. By the end of June, I would say we are working on that. Yeah. So afterwards, you can give it a try. Cool. We do have tutorials, so you can try all your own data, or can try our toy data with the techniques I just described here.
So would that be general to work with other machine learning methods?
Oh, it's a general one. You can actually, for example, the multitasking neural network is a pretty complicated architecture. You can choose whatever architecture you like, right? Number of layers, how to design a neural network is super flexible. So you can do your own work there.
Thank you.
No problem. Any other questions here? If not, we can move forward. Next slide, please. Here is more details about the multitask learning network in case you didn't get the point here. So from the on the left hand side, from the bottom to the top, given an input feature vector, then is a feature to be extracted. And we have, for example, this is a demo of the neural network architecture we do, right? So for example, you have a shared hidden layer 1, shared hidden layer 2, and then afterwards you have a task-specific layer for different tasks, right? For example, in this case, we have 2 categorical variables labeled as green. We have 1 numerical variables as red. The variable here is actually the parameter, right, for the given model. And then your loss function is a combination of the loss function of classification and regression tasks. For example, you can combine cross entropy plus MSE for regression task, right? So the total loss is going to be loss 1, 2, 3, the summation, or you can do the scale for a specific loss as you like, right? So scale here is used for balancing 2 different type of losses, categorical and numerical, because this is not comparable if you simply sum them together, right? That's kind of, a little bit of details about the neural network architecture we can use, right? But as I mentioned before, you can use whatever architecture you want, right? Based on your own data and also your tune results, because essentially you still have to tune this architecture to get a better results with your time series data. Next slide. Application and results. So yeah, we can move forward. Cool. So the first application is very clear, is how are we going to combine the 2 frameworks into one, right? So first of all, if you can tell me which model is possibly the best model to use, and then you're going to tell me what are the parameters I can use for the given model. You just told me, right? And then that's gonna be perfect. So the answer is actually yes. So we can combine them together. Still, you have the offline training process. You train the 2 meta learners, and you can make inference for the new times data. So just 2 steps. The first step is leveraging the pre-trained classifier and then tell you which model is the best model. And then given that model, you call the second learner, it's a multitask neural network learner, and then tell you what are the parameters you should use for the given data. And then you combine them together, you produce your forecast. And now the question is how this performs versus other typical approaches, right? So here's a table at the bottom. We compared 3 different approaches. The first one is we only use the model selection part. And then after you select the best model, I don't care about the latency. I just run everything. I run exhaustive tuning for the given model. For example, you tell me a RIMA model is the best model. I just run exhaustive tuning for the RIMA model and then get my results, right? The second one, or the green one, is we use model selection. And I just want to use the default parameter setting for that model. I don't have time to tune the model, right? So that's a very naive approach. And the third one is we use both, right? We use model selection and we use hyperparameter tuning for the framework as proposed, right? How it works. And then if you look at the results here, still look at the average MAPE and also the median MAPE and also the running time here is very interesting. So ideally, or this is our expectation, that is the first one works the best, because after you select the model, you do the exhaustive tuning, right? That's upper bound you can do. So this means the first row has the best performed results based on the average of the MAPE. So, and that makes sense, right? And the second one is really terrible because you didn't do any tuning, right? And you just simply randomly pick up some parameter settings or use the default setting, and then you run the model. So you have the results in the second row. But the first row versus the second row is actually a trade-off between accuracy versus running time, because that's a 20 times difference, between the first one and second one, right? And I believe the combination of the SLMS and also SLSPT is a trade-off, right? The trade-off between the 2 approaches. So if you look at the MAPE, it's actually not very terrible. The average one is not very good, but actually the median results is pretty good. But the running time, we achieve the lowest, right? So as I mentioned before, that's a trade-off to achieve the large-scale forecasting. If you only have 1 times data, why bother? You simply run exhaustive tuning, right? It's pretty fast actually, and then you pick up the best one. But if you have 1 million times data, it's not feasible. And the self-supervised learning techniques we proposed is definitely your friend here, right? So that's the first application. Combine the model selection and hyperparameter tuning framework together into one technique. So any questions for the first application we have?
Hey, Sheldon, sorry, I may not be following or maybe miss some information in your previous slides. I'm still thinking this is a chicken and egg problem because like if you don't tune your model, right, how do you know you choose the best model?
Yeah.
In your first step, right? So
that's right. So my intuition here, or my answer here is the better your offline process is, the better the meta learner is going to be, right? For example, if you, let's say if you run very good exhaustive offline tuning for, let's say, 10,000 times the data, I mean, it's slow, right? So it's very expensive, but once it's done, you can simply train the classifier to get a better model. And then in the future, for any new times of data, you can simply use it. As I mentioned earlier, you actually don't have to tune or exhaustive tune 10,000 of times data. Our evaluation is once we got 1,000 times data, your gain of adding more times data for the offline part is actually very marginal. So you simply need 1,000 times data, and then the offline part is not very expensive anymore. But your intuition is correct. So we have to do the exhaustive tuning, offline. But the benefit is afterwards we can do much better or much more for a large amount of times data in the future, right? That's a trade-off. Did I answer your question?
Yeah, I would love to kind of dive into a little bit details if possible, but
we actually have our paper is actually on live on archive, so I can share the archive link with you or with everyone, so you can take a look at.
Thank you.
No problem.
I actually have a question.
Sure, go ahead.
So I think two questions. The first question is, are you actually training one multitask neural network for each type of the time series model? That's my understanding. I'm not sure if that's correct or not. So like say our REI has one model and then Profit has another model, so things like that. Am I saying that correctly?
It's correct. That's right. Because you cannot share. I mean, theoretically you can, right? It's kind of add additional multitasks. But in practical, you can definitely train, or you should definitely train different multitask neural network model for different model. For example, Perfect, let's say you have 10 parameters, but ARIMA you have 3. You cannot share the same model, for that part. For us, yes, we do train multiple models for different individual forecasting model. You're correct.
Thank you. And then secondly, is there a way you can explicitly encode some constraint on your parameters? Say, for example, if your model has 3 parameters and there is some relationship between these parameters, other than the shared layers that may somehow encode those information, is there any way that you can explicitly kind of configure that or kind of how to add that constraint to your model?
I believe there's a way to do, but for our framework, we rely on the shared layer to do the job.
Gotcha.
Yeah.
Gotcha.
Yeah.
Okay, thank you.
No problem. I see 5 messages here. Okay, that's from Mark. That's fine. Yeah, it's all the shares of the paper and also the AX tool I mentioned earlier. Yeah. Any other questions for these slides? If not, we can move forward to the second application we want to discuss, and it's actually related to one of the early questions we had, right? So it's kind of ensemble model augmentation. So how can we leverage the technique into ensemble models, right? So using predicted hyperparameters from our framework instead of tuning all models in the ensemble, right? So if you're going to use ensemble model for time series forecasting job, you still have to tune every single individual model, right? But now, if you want to use 6 models, you don't have to tune. Simply call the multitasking neural network, and then gonna tell you the parameters. And now the question is how good it is, right? Versus exhaustive tuned ensemble model. Similarly, if we look at the bottom table, that's the results we have. We still compare 3 approaches. The first one is we do use ensemble, let's say 6 models, but we do exhaustive hyperparameter tuning under the hood. Okay. The second one is we do ensemble, we randomly select some parameters for all of those 6 individual models, for example. And the last one is, hey, let's use SSL, hyperparameter tuning techniques, and then simply tell me what are the parameters I should use, and then combine with Ensemble, right? So how it works. And if you look at the table, we actually have a similar performance, but actually the third row is much closer to the first row. The first row is actually theoretically the upper bound we can have, right? So the average MAP and also the median MAP is pretty good, right? Especially the median number, 0.9 versus 0.11, right? It's super close. But if you look at the running time, Ensemble plus exhaustive tuning, if you denoted the running time as 120, and actually the Ensemble plus our parameter tuning techniques actually 6, right? It's still 20 times difference between your best approach versus the approach we have. Still, it's a trade-off, right? If you have one times data, no need to run the hyperparameter tuning. You can simply do the exhaustive tuning and then pick up the best one from for your data, right? So that's the second application we have. I hope this answers one of the previous questions we have regarding to the Ensemble model. Any questions for this one? If not, we can move forward. Next slide, please. Future directions. So I actually list 3 future directions. Actually, some of them are still, actually ongoing work we are working on. The first one is, combine model selection and hyperparameter tuning into a single model. It's not 2 separate models anymore, right? Right now we have to use 1 classifier plus 1 multitask neural network model. And in the future, we're going to combine them together into a single learner that can do the end-to-end work, right? You don't have to train first and second one, you train them together. So that's the first approach we're working on. The second one is how self-supervised learning integrated with Ensemble model in production. This is something we're currently working on actually. The third one is how to extend it to other types of domains, such as anomaly detection. That's also something we're currently working on, even though it's still in progress, but some early experiment results is really good. Pretty much like you don't have to tune your anomaly detector anymore. You can simply use the self-supervised learning techniques to pick up the best anomaly detector for you. That's based on our internal evaluation with our internal data. So those are the future directions. Actually, some ongoing works we are working on. Next slide, please. I'm not sure if I have any more slides to discuss. Okay, acknowledgement. That's very important. So we would like to thank all the collaborators, especially my intern last summer, Pei, who is a PhD candidate in statistics at Purdue University, and she's going to join us full-time in September. Ginger, Nicolai, Johnner, Peng, and Yang, all the collaborators, we are working together, and those folks are also working on extending this framework into other domains, like what I mentioned earlier in the previous slides. I believe this is everything I have for today, right? I'm ready to answer any questions for the work and also for Facebook at large. Thank you.
Oh, thank you, Xiaodong. I think this is a great presentation, and also thank you, Nick. I'm definitely going to check out the paper tonight. So I think due to the time concern, we only have 5 minutes left. I guess we can probably take the last 2 to 3 questions, and then before we wrap up for the night. Any questions?
Yeah, one question here. Hi, Xiaodong. In your future work, the roadmap about the anomaly detection, can you talk a little bit more about it? Yeah.
It's a good question. So internally, we actually developed a set of anomaly detection techniques. So some of the statistical methods, some neural network based methods, but you have to tune, right? Given you have the true label of your anomalies on the times data, you have to tune certain parameters to make the anomaly detector works best for your times data, right? And then the context is actually very similar to forecasting domain, but the challenge here is actually the true label of the anomalies. Usually, you don't have the truth, right? And the good thing here is internally we do have the platform to the anomaly detection. In that case, we have the true label logged into our database. so that we are able to train the meta learner to pick up the best anomaly detector. For example, our internal platform, the user can come into the UI and say, hey, I have the times data, just monitor the times data, tell me if there's any anomalies in the future, right? But you have to pick up the method you're going to use. And then that's where the meta learner come into play. In that case, you don't have to choose. I'm going to tell you, given the data you have, which one you should go with, right? So we're going to integrate into this one into the UI so that the user, they don't have to do their own homework, right? And also the anomaly detection techniques are going to be open source as well, together with our other forecasting related techniques in the library I mentioned earlier. So stay tuned. But I don't think we're going to open source the meta learner part for detection because that's still in progress. Hopefully we can release that part by the end of this year or early next year.
Oh, that's awesome. Yeah, really look forward to that. And
yeah, thank you.
Yeah.
It's a good question. Thank you.
Bring that work to us, present another time in the future. Yeah, thank you.
Cool.
We will make sure to let the group know when the open source release comes out.
Yeah, I'm actually working on the tutorials, so make sure you got to go tutorials for our library once we open source.
Nice.
I have a question that's not like directly tied to what you guys presented today. Maybe something related to what Mark mentioned earlier regarding like how the data science job family are set up in Facebook. Like you have people focus on research and people focus on product. So is this a trend that you guys are seeing, like data scientists needs to be kind of specialized because you have like a brilliant data scientists like Sheldon creating all these packages, people can just call them. So you don't actually need a lot of data scientists doing a lot of coding. So like, is that something that you guys are seeing as a trend in Facebook or even in the industry that, like data scientists has to pick either very close to business, it's almost like a PA product manager role, and then some other people will be focusing on research and engineering?
I can take the question if Mark and Nick can chime in later. So I guess for the domain of time series data, I don't think we will only need the type of person who can write the package, because we do have a lot of business partner teams. In that case, we need a lot of people to really understand their data, really understand our algorithm as well, and then present the results we have. So pretty much like for time series analysis, we have a lot of folks working on developing the tool. In the meanwhile, we have more folks working on delivering the forecasting results to our, let's say, business partners, right, to really make the real world impact. So that's just a different type of work we have from my observation. For example, the library, I'm not the only person who is working on the library. We have, I guess, about 10 people working on developing this library, but we have way more than 10 people who are working on forecasting related projects and deliver the forecasting results to make a real business impact, right? And it's just a different type of work, I would say. But Mark or Nick, if you have other stuff.
I think the tooling continues to improve that we have to do our jobs. Yet, if there was a theme to both presentations to tie them together, it's that scale causes us to need to be creative and innovative. And so I think there will always be an evolution of technology that brings about new opportunities and challenges to solve problems in new and creative ways. I don't know that we're going to solve that. I kind of hope not.
All right, guys, I think we just reached out of time here. And then thanks again, Mark, Nick, and Sheldon for joining us tonight. And then this is great stuff. And thanks again for joining everyone. And then hope to see you next time at CADSEA. All right.
Thank you so much, Mark.
Thank you for having us.
Nick and Sheldon, great presentation. Talk to you later.
Thank you.
Have a good night. Thank you. Bye-bye.
Good night, everyone.
Take care.
Bye.
Bye.
Good night, everyone.
Thanks.